Okay, thank you very much. Yeah, thanks a lot, Tomek, Livia, and other organizers to organize this nice workshop. And yeah, I will talk about some. Now it's kind of been several years of a program to attempt to do some resummation in planar n equals 4 super Young Mills. So he will restrict directly here to planar n equals 4 super Young Mills. And yeah, for a long time we have been studying integrands in this theory. And yeah, so other people studied integration and symbols. Yeah, there are experts on this topic here. But I always wanted to do to resum something to all loop orders. But with integrands, it was kind of pointless. You cannot resum integrands. And not only that, we could even calculate that we still cannot calculate integrands to all loops. Yeah. But there seems to be at least a new way how to organize things and do this resummation. And this organization is in terms of these negative geometries. So there is kind of new expansion for integrand, but we will see that once you have integrand in the right form and right objects, sometimes you can do this next step. In our case, it's not the integration itself, but it's finding some differential equation that we can solve. And then we can solve it, you will see. Yeah, you can kind of solve it to all loop orders. So it will be this new expansion in terms of negative geometries. It's not something very deep. Yeah, it's very similar to the original definition of the amplitude-hedron for the loop integrand of the amplitude. But these objects are nicer, or not nicer, but they have certain properties that we like, because obviously, even if we can calculate the integrand of all loop orders, we would have to face IR divergences directly, loop by loop order. And yeah, we don't want to do it. So we will actually use this and define some IR finite quantity, which is also not new, appeared in the literature before. It's a Wilson loop with Lagrangian insertion. It's very interesting that it kind of directly sits in this geometric picture for the loop integrand. Yeah, that it's the same object studied before for different reason kind of sits here as well. So we kind of arrive on that independently. Now, just we do only 4-point here. Yeah, so 4-point n equals 4 super Young Mills in the planar limit. We know that something is special for 4-point anyway, because we have BDS ansatz. We know that in principle, we can calculate a 4-point amplitude to all loop order. The kinematical part is just exponential of the one loop amplitude. There are at least some unknown quantities like gamma cusp. We know gamma cusp from integrability using BES equation. But from amplitudes, we don't know. We cannot calculate it from amplitudes. So actually, something underlying this project is actually find a way how to calculate gamma cusp from amplitudes. Yeah, or get to it, see how the amplitudes would like to expand the gamma cusp as well. But yeah, we will calculate the whole object. But there is not only gamma cusp, there is also the collinear gamma cusp at the subleading order. That is regularization scheme dependent. So for that, we don't even know kind of how to approach that problem. Anyway, so our object would be indeed 4-point amplitude. So that's what we start. We arrive at this Wilson loop, but I will explain it in details in planar n equals 4 super Young Mills theory. Yeah, so just a reminder, kind of schematically, we know that the 4-point amplitude exponentiates, so we can resum to all loop orders the individual L loop contributions from, let's say, okay, modulo some rescaling prefactors, and it will be given by the exponent of the leading P. Okay, well, let me already write it now in the expansion. So for us, yeah, so okay, sorry. So there is an exponent of some 1 over epsilon square pieced where gamma cusp is sitting here. Plus, there are subleading orders, and they capture kinematical dependence as well, and that is given just by one loop amplitude. But for us, it will be, at least the motivation would be to access this piece. So in a very simple way, if we take the logarithm of the amplitude, it already starts directly as gamma cusp plus some subleading piece at the leading 1 over epsilon square order. Unlike the amplitude, if we expand it term by term in perturbation theory, it would start as 1 over epsilon to 2L. But most of all of these IR divergent things would come basically from products, exponents of the lower loop. So the really new thing sits only at 1 over epsilon square order, very deep down in the 1 over epsilon expansion. Okay, so so one of the motivation, or which object we will eventually work with, is this relation for the logarithm of the amplitude. And the logarithm of the amplitude, that's something we can also think about at the integrand level. Yeah? So of course, normally we would just take the amplitude, take the logarithm. This is already post-integration. But we will see that the integrand of the logarithm also makes sense. And the integrand of the logarithm will be very special because it's almost, after you do the integral, it's almost IR finite. Only at the very last step of the integration it produces this divergence. And we will use it to define this IR finite quantity because we will not do the last integration. That would be the whole point. We integrate everything out except the last piece, last loop, and therefore it stays finite. Yes? Yeah, we will derive the integrand. Yes, yes. Yeah, we will derive the integrand, and the integrand will have such special properties, which just mimic the properties of the logarithm, that you will see that there are no divergences once you start to integrate loop by loop, only after, well, only when you decide to integrate the last loop, then it produces a divergence. Yeah, so I can already say it here, that we will define then some, I'll call it f function, of it will be function of only one variable. Yeah, we will see which variable it is, but unlike if we do amplitudes, if we do ratio functions, remainder functions, functions of many variables, this will be only function of one variable, which simplifies our life dramatically. And this would be an integral of the logarithm of the amplitude when we integrate over everything except the last loop. Yeah, so kind of L1 up to L minus 1. And that variable will depend on this last loop. Yeah, it will enter that. Yeah, for experts, they already see, because with 4-point you cannot make any dual conformal invariants, but once you add the loop, you can, and there is only one. Yeah, so. Yeah, so I'm not very, yeah. Yeah, sorry. So let me delete 4 label, because we are still doing 4-point anyway. The 4 was supposed to be 4-point. Yeah, there is no label. So there is a full amplitude once you resum all loop contributions, if you can. Yeah. So this will be kind of integrand. So yeah, this will be an integrand of it. So let me say integrand. Yeah, this is an integrand for the logarithm. Yeah, so the logarithm of the amplitude at a fixed loop order, L. Yeah, so, okay, maybe I should be. Yeah, let me explain. So we have the logarithm of the amplitude. We can also expand it in the perturbation theory. So, so this is logarithm of the amplitude. We have some contribution to it. Yeah, so logarithm of the amplitude at L loop order. Okay, and we are summing over, well, I guess here it's 1. And this object you can also write as an integral of d4 L1 up to d4 LL of some integrand, L loop integrand. And now we decide not to do all integrals, because this is still, unfortunately, IR divergent. Still goes like this. But if we only integrate d4 L1 up to d4 L minus 1, the same object, this is finite. Yeah, only the last loop integration causes the divergence, and this will be object that we will then denote FL, Z at L loop order, and we will resum these objects. They are finite, so in principle you can multiply them by coupling constant and resum. It's finite. Right, so this you can see. Well, you can see it in the structure of cuts here of this object, that you will see that the only way how to generate, go to a dangerous region when the IR divergence comes from, you need all loops to participate in the integration. Yeah, so there is an integrand level understanding. There is no theorem. Yeah, there is no theorem that this means the same thing as the integrals, but we kind of know where the IR divergences come from, and the property of this integrand is exactly such that in order to generate IR divergence, again, for experts, you have to take the loops and go to the collinear corner of the external kinematics. You need all loops to participate. And if we freeze one of them, then this will not generate IR divergence. Yeah, James has.
To clarify some of it, if you expose it in the Wilson loop language, the object you want is a square loop.
Yeah.
That's the correlation.
Yeah, that we will arrive. Yeah, that's, yeah. Right. Right. Just the. You can take it like that. The thing is that the fact that the logarithm of the amplitude integrated is the same as this correlator is a small mystery, I would say. Reminds on that. From this point of view, it is unclear, but the geometry calculates both objects at the same. Yeah.
But then on the other hand, the way that you're going to get the integrand doesn't necessarily either rely on.
No, neither of that. Yeah, I am. Yeah, the object that I am defined, I am free to claim that it calculates whatever I want. Yeah, because it doesn't rely again on the definition. Neither of them, neither Wilson loop nor the amplitude. Yeah. But the answer to your question is yes. It must be the case that you can integrate here in any order you want, unless you start to hit divergences, then it's subtle. But you don't hit divergences here. Yeah. But as James said, from the Wilson loop point of view, this thing will correspond to insertion, so you actually don't integrate over the last. It's finite all the way from the definition. Okay, I kind of went very, very far in just the motivation for the thing. Yeah, more questions? No. Yeah. Yeah. No, I will not. Yeah. We will not use any properties on Wilson loop. It's just that the object we happen to calculate is the Wilson loop. Yeah. But we are not putting the gamma cusp in it at any point. Yeah. So we are not using that information. Okay, very good. So but we will not. Okay, so maybe still in the motivational part, we will not be able to calculate. So this is in the perturbation theory. Of course, you can then define. So this would be order by order in perturbation theory how to get something finite out of our picture, and then we will resum. And we will define some object which depends on coupling and this kinematical variable. We'll talk about later in more details. And again, we just dress the L loop contribution with coupling and then sum over all loops. Okay, so this is the object that we would like to have. We would like to calculate. We will be not able to calculate it. This is just too complicated. Yeah, too arbitrary order in coupling. But if we had it, then we can go to weak coupling. At weak coupling, nothing interesting. Yeah, it's just what we would expect. We would kind of capture the perturbative series. But at strong coupling, which we never went to strong coupling in these geometric pictures for amplitudes, we have no idea. Well, we have idea from ADS-CFT correspondence for what happened for this full object, There is a expansion at strong coupling. The leading order is known. Also, Radu was working on it like 10 years ago, some work. And but the expansion there is extremely unclear how to actually perform. The thing is that here, the expansion at weak coupling is just expansion in G square. So there is a G square piece, G to the 4, G to the 6, and so on. The expansion at strong coupling is the 1 over G expansion. Yeah, there is a term which goes like G, then 1 over G. Okay? So of course, here we rely on the fact that in planar n equals 4 super Yang-Mills, the perturbative series is convergent, so we can actually, it's not asymptotic series, so we can actually resum the contributions, and there is no, there are no non-perturbative contributions here. So, but nobody has done ever this. Yeah, of course, there is calculation at weak coupling, which is just our usual calculation using, integrand, integrals, unitarity methods, normal things. We will do it in this geometric picture, but it is calculating the same thing. At strong coupling, from ADS-CFT, the minimal surface, and that looks very different from that. But we would like to see the interpolation. Of course, this object is too complicated. Even if we can calculate the integrand to all loops, which we cannot, we would be not able to integrate it, and so on. But we will do some approximation, so that's the whole point of doing it. We will do some approximation of each perturbative piece, FL, Z. We will approximate it by some at each order in perturbation theory. And we will be able to calculate it at each order. I will explain exactly what I mean by this approximation, and then we will resum these pieces. It will be, from the physics point of view, it will be very ad hoc approximation, and there is no guarantee that this resummation gives anything interesting. But as it turns out, there will be something interesting there. Yeah. No, it's convergent. Yeah, well, yeah. Well, if it, well, you have to try, right? We don't know a priori, yeah. So, well, this is not a completely new idea. So this was already done at the level just Feynman diagrams. There is a resummation of ladder integrals that we can do. What? It's a kinematical variable. Well, no, it's real. Yeah. But yeah, I haven't defined it yet. Sorry. I'm just trying to say where this is going, but then we will do it properly. I just want to motivate here that the resummation at the level of just Feynman diagrams was done of ladder integrals, because you can ask the same question, can I resum anything in just usual way how to expand the amplitude in terms of diagrams. So the ladder integral can be calculated. Exactly, it was done in a little bit a different setup of phi cube, and yeah, these things I believe were massive because the thing must be finite and so on. But anyway, so this is basically some dialogue. But we are not really interested so much on the kinematical part here, because as a function of kinematics would be more complicated, but we just want to see how it scales as G. And if you resum these ladder integrals, you multiply them by coupling and resum from 1 to infinity, then at strong coupling, they go like e to the minus G. Yeah, which is kind of very bad. It seems that the approximation is extremely bad, but you expect it. This is just some completely ad hoc thing. Because at strong coupling, it should grow like G and have 1 over G expansion. And instead of that, it just is exponentially suppressed. Yeah. So this just says that any approximation like that should kind of lead, should be bad. Yeah. Yeah, yeah, I think there were yeah, this is in the Broadhouse Daviditchev. They are massive. Yeah. Yeah, yeah. Well, otherwise there is IR divergences. Yeah, so. Yeah. Yes. Why I recall, I think each integral is a dialog, right? But you can write it in an integral representation, and then you can resum it. Sure, sure, sure. But we are here just looking, yeah, it's not the same function. I'm not saying that we are getting the same function. I'm just saying that at large G, there is an exponential suppression. Of course, it depends on two variables and so on. But here we are just looking at how it scales with the coupling. Yeah. So no, I just want to say here that from this example, which was done a long time ago, it seems that ad hoc approximations don't work. Yeah, I'm resumming piece of the answer that I know how to calculate. So this is kind of a negative result. Well, we will do exactly that. Yeah, because not that we don't want to calculate the whole thing, but we just don't know how to do it. Yeah, it's too complicated. Yeah, I don't know. Has anybody done that? Or, but that, I don't even know. Is the tennis court kind of known for general? So we can have like a more. We can have kind of this extension of tennis court, but that looks too complicated. This one is probably hard, but we can also have kind of this one. But I don't know. What? Ah, okay. They are all the same. And they were resummed? Ah, okay. But has anybody resummed them, or? Maybe there is a different. Well, if it is the same, then it's again will be exponentially suppressed, most likely. Yeah. Okay, okay, okay. Yeah, there are other ones. Yeah. I don't know. Has anybody resummed them? Okay. They are also exponential. Sorry, sorry. So I'm not educated. I didn't know that it was resummed, but double pentagon must be higher, higher number of points. Yeah, it's not even 4, right? 6.5. Ah, okay, okay, okay. Okay, great. Yeah, so you see these resummation are, yeah, typically don't work. Anyway, but we will resum, but I just want to say a small spoiler. The simplest geometries we will resum will look like this. It will be not these diagrams, but kind of the spirit will be similar, and we get the same thing. However, there will be already something interesting in the contribution to gamma cusp. Yeah, because one thing is to calculate the whole object as a function of z. That's complicated. And the other thing is to just ask, what is the contribution to gamma cusp? Because as we said here, actually, there is a relation. The FLZ knows more than just gamma cusp, yeah? Because if we integrate it over Z, we extract, we have one leading order would be gamma cusp over epsilon square, and there would be farther pieces, 1 over epsilon finite piece, and so on. So obviously, the FLZ knows about L-loop gamma cusp, yeah? So we can either ask the question about calculating this FGZ, but we can also ask a simpler question of just calculating gamma cusp. Yeah, and we can extract the gamma cusp from the FGZ. So I just want to mention it because in our attempts, even if we fail to approximate in any reasonable way the strong coupling behavior of that by our ad hoc approximation, we will still get something interesting for the gamma cusp itself, which kind of lies can be obtained from integrating that. Yeah, so just say that inside there is sitting the gamma cusp, yeah, of that function. Okay, yes. Well, yeah, but the log m itself is not dual conformal invariant because it has divergences. So yeah, it's a function of more variables. But our function fz is dual conformal invariant. So it will only depend on one cross ratio. So fz will depend only on, sorry, only on z. I will explain. Integral of f, this. Well, then you hit IR divergence, you have to decide how you regulate it. And you have to break dual conformal symmetry. Yeah, here it's dual conformal invariant. I didn't get to dual, but yeah, this is dual conformal invariant, so it's very restrictive. It only depends on one loop and 4 external momenta, and there is only one cross ratio you can cook up from that. Yeah, in momentum twisters, it's kind of obvious. Yeah, that it's only one. Yeah. So yeah, but once you integrate, it will start to depend on more variables. You break dual conformal symmetry, it starts to depend on Sij's and so on. But yeah. Okay, good. So so now let's start from the beginning. Okay, I took half an hour to introduction. Okay, I will not start completely from beginning. I will not talk about Park-Taylor factor, how things are great. So I just start with what we need. So yeah, so we start with the 4-point integrand. So our data, kinematical data, are external, external momenta, but because we are in planar n equals 4, we will use momentum twisters. So we have Z1, Z2, Z3, Z4. And we have loops. And loops ABI, where I runs from 1 to L. So these are lines in momentum twister space. Yeah, and these, and that 4-point, okay, doesn't matter. Well, you can visualize it as forming a tetrahedron in P3. Because it's 4-point, then yeah, there is no restriction on these z's. Yeah, they can be actually fixed to be just unit in projective space. Okay, now so the integrand is a function of these variables. It's projective. Yeah, so the integrand depends on these zi's and abj's at L loop integrand. And yeah, and it is projective, so if we rescale the z's or the ab's, yeah, it has zero weight. Yeah. Anyway, so at one loop, as we all know, this is just given by a box integral. Which in momentum twister space is written as AB12, AB23, AB34, AB14. There is a normalization, and there is a measure. Okay. Of course, we know all that. But now just the way how you get the integrand from the amplituhedron. So it tells you that there is some space of these of a single line AB now. It's a 4-dimensional space. And the space is bounded. The AB line satisfies certain inequality. So all these AB12, AB34, AB14, AB3, sorry, 2, 3, 3, 4, 1, 4 are positive. And also AB13 and AB24 are negative. This is the definition of this space. If you then expand A and B as 2 points along the line in terms of these external z's, so I have it plus x z2 minus z4 and z1 plus y z2 because that's z3 plus w. Yeah, this is just expansion in a basis. Then these inequalities say that our 4 variables which define the space are just positive. Yeah, so this is a very simple space. It's a 4-dimensional space, but it's like a positive quadrant. And then the integrand is a form with logarithmic singularities on boundaries, but this space is just x, y, z, w is positive, so the form is just given by this simple form. And if you change the variables back from x, y, z, w, y, small z, z, w, back to the momentum twisters, you just arrive at this form. Okay, this is the definition of the space in terms of AB. The AB is a line, must satisfy certain constraints. You can choose parametrization, you can choose another one, not this one, any one. But this one is particularly simple because once you plug AB here, these conditions just gives you x, y, z, w is positive. It's very simple space. Then the differential form that we associated with that is just this simple form. If you solve for x, y, z, w in terms of a, b, and z, you back then the one loop integrand. Okay? So this is one loop. Two loop is already more interesting. Of course, we know these integrands up to certain loop order, but the thing that we will use for kind of all loops is this definition. This amplitude-hedron definition, and we will then do the simplification. So two loop, in the standard way, we know that this is actually sum of four double boxes. Yeah, note here that A, B, and C, D are different, so we really have to sum over 4, not just 2. Yeah. Because this is for the integrand, so the whole thing must be symmetric in A, B, and C, D. So we know that this is the right answer, but in momentum twister space, we can just read off the integrand from that. Here there are no non-trivial numerators. CD to 3. And then there is this propagator ABCD. The ABCD stands for this internal propagator. That's a crucial kind of point here. Yeah, the ABCD propagator. And then there is some normalization, cube. And there is some measure in this line A, B, and C. It's the same measure as is over there, but I will not write it explicitly. Measure. Okay, so just the double box integrand. Now, in the amplitude-hedron setup, we have space of 2 lines. So line AB and line CD. This is 8-dimensional space. Each line has 4 dimensions, so this is 8-dimensional space. And each line satisfies these one loop conditions. So let me just denote them one loop, such that I don't have to write them again. So AB satisfies one loop, CD satisfies one loop, but if we didn't impose anything else, we just get one loop square, which would be a box square, yeah, which is perfectly fine space, but it's not a 2-loop amplitude. But on top of these, we have to entangle these loops together. They are obviously entangled in the double boxes. And the condition is that ABCD bracket is positive. Yeah? But while in this parametrization, these conditions became kind of trivial, just X, Y, Z, W are positive. So if we denote with label 1 the same variables for A, B, and with label 2 the variables for C, D. This is still true. They are all positive, so 8 positive variables. Again, this is a very simple space. If it was just that, we would just a trivial form and we could add 1 loop square. But this condition makes it complicated. And this condition kind of puts constraints across these two regions. And would impose some quadratic or bilinear inequality between the variables of the first loop and the second loop. Yeah, so so the mathematical problem is give me all x, y, z, w, these 8 of them, such that these inequalities are satisfied. If it was just this, it's trivial. It's just kind of a positive not quadrant, but whatever, in 8-dimensional space. They are all positive. But this quadratic inequality makes it complicated. Yeah? Because if you just put random positive numbers, this might be not satisfied. So you have to you have to triangulate the space. That's the problem. You have to triangulate the space. This is a non-trivial space. And once you triangulate it, you calculate the form for each piece, and then you sum them. And you get some non-trivial form. So in terms of these variables, this was for 1 loop. So for 2 loop, in these variables, you have these guys in the denominator. Then you have this A, B, C, D. So let me not expand it. Just I leave it here as A, B, C, D. It's this is this thing, which will be sitting in the denominator. And then there is some numerator. And the numerator has 4 pieces. x1, w2, plus x2, w1, plus y1, z2, plus y2, z1. Okay? So that's what you get if you triangulate, sum the pieces. You get this form, and this form is nothing else. If you expand the numerator, you can cancel the numerator against denominator, and this is just 4 double boxes. Yeah, if you just write it in this form. Yeah, because here we use the parametrization, but then you can again go back to A, B, C, D, and each piece in the numerator is one of the 4 double boxes. Okay. Yeah, the only step I didn't say is how to solve these inequalities. Yeah, but anyway, basically what you want to do is to consider all possible cases here in this quadratic inequality such that the x, y, z, w labels have fixed boundaries, are from here to here, from here to here. Once you know that, this kind of defines a simplex for you in this space. This is not a polytope, it's not exactly simplex, but kind of simplex in this. This is a Grassmannian space. And then you can write a form. Yeah. But exactly you have to kind of consider all possible cases in this inequality, which gives defined ranges for each variable. Yes?
Once you've defined your space with the inequalities,
right.
is undergo unique?
Yes. Yes.
Is there some kind of theorem that you're using that guarantees that?
Well, the thing is, well, it is unique. Well, it was proven it was unique in some math papers, yeah. But okay, but let me give you some like pedestrian way how to think about it, yeah. So one thing about uniqueness is guaranteed even by just the dual conformal symmetry, yeah. Because the thing that when the problems would be non-uniqueness is when you don't have any poles, but you cannot have a form with no poles, yeah. Just because you just polynomial in these variables or these brackets. This is not a good projective form. But also just by construction, yeah, because you cut it into pieces, each piece has a D-log form. So you just sum these D-log forms together, yeah. The non-uniqueness, and it's again, and everything builds on the D-log form with logarithmic singularities. The only way how to get something non-unique is that the singularities are not logarithmic, right? Because you have to be able to cut it through. Yeah, to go to the lowest codimension boundary. Yeah. So the only thing non-unique would be that you can add something to this, But once you add something to this, you start to change the boundary structure. But the form exactly should reflect the boundary structure of your space. Yeah, this is not a kind of mathematically precise way. Well, mathematically you have to first prove that there exists a differential form at all. But that's actually a non-trivial thing, but we know that the amplitude is exists, yeah. Yeah, again, in our case, the construction might be explicit using the triangulation, yeah, because for each kind of a simplex, which is given by 8 inequalities on 8 variables, we can always find a unique differential form, yeah. It is complicated, yeah. So I wrote it like that, but the double boxes actually don't triangulate the space in any natural way. They do externally, yeah. But it is actually more subtle. I look at it in the past, but yeah, it triangulates this externally, but it's not clear if it triangulates the amplituhedron itself or some other space which has the same differential form, but a different geometry. I think it's the second one actually. Yeah. So therefore, there is some mystery. Yeah, there is still some puzzle. Because unlike for the tree-level cases, when there are external triangulations, at loops there seems to be some sort of obstruction. Yeah. Yeah. No. So A, B, C, D are loops, L1 and L2 in momentum twisters. A, B, C, D is this. It's this, yeah, I just didn't wanted to write it here, I just wrote A, B, C, D. It's this, yeah. If you plug this parametrization that I wrote here for A, B, and C, D, you get this, yeah. Yes, indeed, yeah. Right, yeah, it's one inequality. Okay, so this is a 2-loop at L loop. The definition of the space is very analogous to what we have here. You just have to impose these quadratic inequalities between any 2 loop lines. So now I like to use A, B, C, D, E, F, G, H, but for general L loop we have to just use label A, B, I. So we are at L loops. So these are the loop lines. I is from 1 to L. And then the statement is that ABI is inside the 1 loop amplituhedron, which means that it satisfies this set of inequalities. So this C1 loop ABI plus any pair of loops. This bracket is positive, which puts a bunch of these type of conditions between any pair. Yeah? So in the end, we get L choose 2 of these quadratic inequalities. And that's a lot, yeah. So this is a very complicated space. It's 4L dimensional space. We have variables xi, yi, zi, wi if we choose this parametrization. They are all positive, but in addition, they satisfy the inequalities that we had here. Are positive for any pair of I and j. Yeah? Yes? Yes. Right, yeah, so that's not transparent at all. Yeah, so yeah, you are exactly right. We a priori know if we are interested in the differential form, which we are, we a priori know what are all the propagators in that form. Yeah, so it's all these external propagators like ABI 1, 2 up to ABI 1, 4. And then there are these ABI, ABJ. And there are for all pairs. We know that if we, and then there is some gigantic numerator. We know that if we expand it in terms of diagrams, we cannot preserve all ABI, ABJ. Some of them must cancel. I think even at 4 loops, we would have 6 propagators naively, but there is only a diagram with 5. There is no diagram with 6 propagators, internal propagators, right? So yeah, so this is, once you expand it in terms of kind of local objects, yeah, many propagators must go away. Also, these must go away, yeah, because even in this double box, the ABCD was the same, but always 2 propagators cancels. AB34 is not here, and CD12 is not here. Yeah? So there is a cancellation between numerator and denominator. But yeah, the geometry kind of gives a very different type. If you triangulate it, it gives a different type of expansion using spurious poles. It looks more like BCFW. Yeah. If you put it under common denominator, cancel all poles, they are just all of them there. Yeah. Yes. No, no. So the BCFW, if you triangulate, it looks like BCFW. It's not exactly BCFW. Unfortunately, at loops, the BCFW likes to relate the amplitude to lower loop amplitude with higher K. However, this object doesn't know anything about 6-point NMH. Of course, it does. On single cuts, it does. But once you triangulate it, I don't know how to use that intuition. Yeah. While BCFW critically uses that. It takes a 6-point NMHV L-1 loop amplitude, glues 2 legs together, and it gets the 4-point loop. But in the actual triangulation, these pieces look very weird. Yeah. No, the triangulation is like very geometric. Yeah, you just really solve the inequalities, but it has nothing to do with any physical expansion. Yeah, even this case of 2 loops, if we do it, it would be not that hard, but it would eat up the rest of my time. You would just break this thing into 8 pieces. They kind of look all the same, these 8 pieces, and you sum them. They have some spurious poles. You cancel them, and you get that. But this doesn't look like BCFW. Yeah. Okay, so this is our space. I just want to say here that we have a definition of this geometric space for the integral to all loop orders, but doesn't mean that we can calculate the form to all loop orders. Yeah? It means solving these inequalities, which is kind of hard. At least for me, it's hard. But we have a definition of the space. Yeah. So usual thing with unitarity and Feynman diagrams, it might be as hard as this, as the actual computation, or even simpler. This might be even harder, but it lacks kind of the definition. Yeah, what is the definition of the integrand? It's a sum of all diagrams which satisfy all cuts. That's fine, but here the definition is, you can more work with that, even if the step of calculating the form is hard. Yeah. And this is exactly that we start from here, and now we do some simplification, which makes the problem of calculating the form solvable. And as you can already imagine, the main bottleneck, why the geometry is so complicated, are these inequalities, these mutual inequalities between ABI and ABJ. Yes? Yes? No. Sorry, Mattia. The thing is that here, even if we succeed, we just get the integrand. But it's the same integrand as you would get from unitarity methods. So if you really want to integrate it and gamma cusp, it's kind of outside. Sure, but this was, but but Nima had some tricks how to get IR divergence from the actual integrand, yeah. But, yeah, that was his paper with Aaron Hillman. Yeah, but this was not related to trying to do something to all loops and some simplification. This was for any integrand, yeah. If you just give him integrand, it didn't have to come from any geometry. Yeah, but here in this story, we are in the end calculating, if we want to solve the whole problem, we would just calculate the same integrand you would get from unitarity methods, and which was calculated up to 10 loops by Jake. But the thing is that first for us, it's even hard. The 3 loop we did, but even 4 loop, which is not that hard using unitarity methods, it's hard to solve these inequalities. Yeah, so obviously solving the whole object yeah, it's okay. Again, I would say just hard, and this is not at the moment what is it good for. Yeah, but the fact that it has this definition, it's good for to do some ad hoc simplification, which allows us to solve the thing. Yes. Well, the contour, yeah, it's not part of the story. So you have to take the integrand that you get if you want to integrate and just go back to momentum space, integrate D4L. You can translate the contour to momentum twistor space. It's a complex contour. Yeah. The contour doesn't look natural, but I don't have anything more to say about it. Yeah. It's not part of the story. Of course, there is now some idea that you take the integrand, integrate it over some other region somewhere. And can you get a amplitude or can you get some interesting function? I don't know. Yeah, there are these Ayamoto polylogs. Nima already had it in his paper about positive geometries, and then with I think the paper with Alice Yuan on the cylindrical contours. So there is to do something with integrand, integrate it against something else, but really the physical contour is some complex contour, which doesn't seem to fit in the story. Yeah. Okay, good. So. Okay, so I think we will not write more formulas for integrand, so we now turn everything into some figures. And hopefully it will be clear what type of simplification we do. So the L-loop integrand in this amplitude-hedron setup is given. You can, for example, that. You can graphically represent it as a completely connected graph. I explain what are the lines and what are the vertices, and this. So each vertex is one of the loops, AB1, AB2, AB3, AB4, AB5, for example. And this is each of the vertex, and each of the line is this mutual positive relation. So AB to AB3 is positive, is represented by the edge. Okay, so 5-loop amplitude-hedron geometry, we would kind of label it by this picture. These are loops. Each one loop lives in the one-loop amplitude-hedron, so it satisfies the inequalities which I already erased, this C. At each line says that there is a mutual positive conditions. From what we discussed, it's obvious that the complication are these lines. If there were no lines at all, this was one loop to the fifth. Yeah, it would be each loop is separate, doesn't talk to any other loop. If we, for example, consider just this line and nothing else, this would be a 2-loop times 1 loop times 1 loop times 1 loop, and so on. So it's obvious that once the graph is not connected, then it's just a product of two objects. Yeah. So not connected are simple. So if we had this times this, or this graph, then this is just 2-loop times 3-loop. Yeah, because these two talk to each other and these three talk to each other. Okay? The amplitude itself is maximally complicated. Everything is connected to everything else. So now the simplification, the ad hoc simplification says that we try to approximate the amplitude by other objects which have less of these connections. And we decrease the number of connections such that we can actually solve for the integrand. Now, this is not... this comes from doing a following change, so following expansion. So the amplitude is represented by a single geometry, so it's one object. Yeah. So, but we can do a following trick. So if we have a space let's say the line AB and CD, and this means that AB and CD are positive. And we take a union at the level of form is just sum of the space when we flip the sign of the condition to be negative. So ABCD is negative. So ABCD is either positive or negative. Union of that is no restriction on ABCD. Okay? So this is a space when A, B, and CD have no restriction. Well, this one is simple because this is just one loop square. Yeah, I should, yeah, I don't have colors here, so let's do, okay, I do double line, yeah. Huh? No, it's not 0. It's, you have two No, it's, you have a space when some object is positive, the other one is, the other space is negative, so the union is that it's either positive or negative, so no restriction. Okay, well, this was an amplitude, two loop, okay, so this was a two loop integrand. This is a one loop square. Yeah, one loop in AB, one loop in CD. And if you calculate this object, so this is two loop minus one loop square. There is some symmetry factor which comes, anyway, from the fact that this is not literally two loop, this is 2 times two loop, yeah, because we are symmetrizing in ABCD. But this is an integrand for the logarithm of the amplitude. Yeah, so, okay, I just do it with curly. Okay, I'm very inconsistent with the notation. So logarithm of the amplitude two loop. Yeah, we can see it if we did it, if we took the amplitude as 1 plus g times one loop plus g square, or g square plus g to the 4 two loop, and so on, we take the logarithm of the amplitude and we expand it in g, we would get g times one loop, I think with minus sign, so sorry, g square plus g to the 4, and there would be a combination of two loop and one loop square. There would be minus 1/2 one loop square. Again, at the integrand level, there is some symmetrization in ABCD, but for the integrand, this is the correct integrand because this gives 2 times the two loop amplitude. Okay, so but here we got it kind of geometrically at the level of these spaces. So this space is an integrand for the two loop logarithm of the amplitude. Yes, yeah. So yeah, you only get logarithm when you replace the positive condition by a negative condition. We will see that at the higher loops, it's not a single thing, it would be a sum of things. Yeah, at two loop, this is the simplest thing. Now note that here, these are integrands, these are geometries, and forms of the geometries are integrands. If we integrate this, we get 1 over epsilon to the 4, it's a two loop thing. If we integrate one loop square, we get 1 over epsilon to the 4, it's one loop square. But the difference between them is only 1 over epsilon square, right? So this geometry, or this integrand, if we actually integrate it, it would give the gamma cusp two loop over epsilon square. Yeah, it would be zeta 2 over epsilon square. Yeah, so this is less divergent. Now, yes? Yeah. Right. But here, the thing is that these guys, okay, this is actually this. This is a boundary, yeah. So ABCD is 0, is a boundary of the space, and these two guys basically glue on this boundary. No, it is, no, it cancels. The boundary cancels. They kind of comes with the opposite orientation. It's really, yeah, if you're, it's like this, yeah. So you have one triangle and another triangle, and this is the ABCD. So here it's positive, here it's negative. And yeah, if you sum it 0, yeah, Tomek is also right. You can also write a form on the boundary, but it's lower dimensional. Yeah, so it's like on special kinematics. But you will see that if you write a form for this and the form for this, the ABCD pole cancels between them. Yeah, between these two spaces, and it gives just one loop square. The one loop square obviously doesn't have that pole. Yeah, but here anyway, the lesson here is that the logarithm of the amplitude naturally shows up, and also that these negative geometries now, because this line imposes negative condition, are friendly to IR divergences, have smaller IR divergences. Here it was a trivial case, but now if we go to L loops, we can just combinatorically prove that if we start with this diagram and now we kind of replace each positive line by negative line and a no line, everything very nicely organizes itself such that we can identify the logarithm, integrand for the logarithm of the L loop amplitude. So IL, so this is integrand for L loop logarithm. And it will be a sum of these objects, so at 5 loop like the one that we have, which are connected. But not necessarily with all lines. Yeah, you sum over all connected objects. Yeah, so all connected. And these lines, sorry, so these lines are these negative lines. I know that I'm switching the notation back, but because now we will talk only about negative, I define that this line means negative. Yeah, such that I not overburden the pictures. So this is negative lines. Yeah, so we started with a single geometry with positive lines, and for the logarithm we end up with a sum of geometries with negative lines. Okay, but this is already good because there was no approximation for the amplitude itself. It was one thing, but now we have a lot of contributions, and we can decide which one we would like to take and which one to ignore. Yeah, so so for 2 loop, this is given just by a single picture. At 3 loop, we already have this picture, and then we have this picture. Yeah, we are already getting 2 contributions. And you can imagine you just draw all diagrams at higher and higher loops. Now note, so this is a subtle point, but if you study the cuts of these objects, yeah, so these guys are not diagrams, they are not amplitudes, but they are dual conformal invariant objects with the usual propagators and so on. They just don't correspond, they just don't look like diagrams. Yeah. If you want, they have too many propagators. Yeah, you cannot draw them as diagrams. Yeah. But otherwise, they kind of live in the same space as diagrams. But they're just, you cannot just draw them as diagrams. You cannot interpret the sequence of propagators as being a diagram, but the sequence of propagators is the same. It's just these AB1, 2, AB2, 3, and so on. Now, if you would like to integrate these objects, you can study the cuts, and you can make an argument that all of them are 1 over epsilon square divergent. All of them. Yeah. So, and that's exactly thanks to these negative lines. Yeah, they kind of kill all divergences. Each negative line kills any IR divergence. It kind of vanishes in the collinear region when you would generate the divergence. The only case when you get the divergence is that when you integrate over all of them, all of the loops. Yeah. So that is also the crucial point when we go to this Wilson loop. Yeah, picture. Okay, but so far we are not there. So we have new expansion for the logarithm of the amplitude in terms of these objects. And you see that they kind of have some hierarchy. Okay, I just draw a couple of them here. Yeah, there are many more of them here. So as we said before, there is fewer of these internal propagator. These guys are these negative conditions, but at the same time they show up as poles in the integrand. Fewer of them you have, simpler the object is. If you have none of them, then it's just a power of one loop. Yeah. So you can also at two loop there was only one. So this is a logarithm of the amplitude. Even this object is not a sum of diagrams, or not in a usual sense. Yeah. It's not a planar object. You know, we know from this that this is a sum of double boxes minus one loop square. But one loop square is not a planar diagram in a usual sense. Yeah. So these objects are also not planar things in the same sense one loop square is not a planar thing. Yeah. So there was only one, but at free loop we already see there are two contributions. This one has three of these propagators, or these in mutual condition. This one has only two. And this one is simple and this one is complicated. Yeah. And you can see that the complication, which is translates to the number of these lines, also can be counted by number of internal loops in this loop space. Yeah, so this has one or cycle. This has one cycle, this has no cycle. This guy has already 3 cycles at for loop. This one cycle, there will be also things with no cycle. So, so now the statement is that the contribution organize themselves in terms of these geometries with the number of cycles. Or we call it loops of loops, because it's kind of loop in the loop space. It has nothing to do with the usual loops. The usual loops are just given by the number of dots. Yeah, this is 2 loop, this is 3 loop, this is 4 loop. But in this expansion, in terms of these negative geometries, the more complicated geometries have more these internal loops, loops of loops. All of them, all of the connected. All connected graphs. Yeah, sorry, these lines are already these negative. I changed the notation. Here it was positive, this was negative, but in order to avoid drawing everything double line, here all of them are already the negative. Yeah. No, single lines. Yeah, there will be also, I didn't draw it. You draw everything. This one is there as well, things like that which have no cycles. Everything is there, yeah. No, there are no symmetry factors here, but the thing must be symmetrized in all kind of AB1 up to AB4. So for example, AB1, AB2, AB3, AB4, and then you have to symmetrize, yeah, because AB1 can be also here or here or here, yeah. But with that, there are no symmetry factors. If you integrate, there will be symmetry factors. Yeah. Before integrating, it's just a function of all these loop lines. They are all independent and so on, so no symmetry factors. But the integration, yeah, because this graph is not have different symmetry factors than this one once you integrate. Yes?
I think what you're drawing here are different contributions to omega that have propagators between the loop points. If I think of the points in space-time,
Yeah.
Points, integration points.
Yeah.
Yes.
And there's
some numerators.
There are numerators. Yeah.
And it can have zeros when points coincide, or?
Could, yeah. But yeah. So here these things, yeah, represent these geometries. But once you kind of want to give a space-time interpretation, yeah, each line is a propagator, but there is some non-trivial numerator, and the numerator does some interesting things. No. So, okay, so that's a very good point. This would correspond to certain like double poles in the integrand, but they are not there. Yeah. So this type of divergence.
It doesn't have to be a double pole in the integrand. It could just be you've got lots of single poles that all add up when all the internal points collapse together.
Where the internal...
double propagator is not the only divergent topology. In fact, the first one on the bottom line, unless there are some zeros in the
No, there are zeros. Remember, even the amplitude itself had all propagators. but they were cancelled by numerators in case you would like to expand it. This is the same thing here. Yeah. So there is nowhere higher in the same sense. Yeah, in the same. You have to impose all the conditions, so you start with all of them. But yeah, but it never happens that kind of you will have enough of them to cause a problem when they go to the same space-time point. Yeah. So this positive negative actually doesn't change anything into that. Yeah. But that's a very it's a good point because the numerator must guarantee that, and this is one constraint on the numerator that exactly does this. Yeah. They are not diagrams now. Yeah. I don't know. If you partition fraction, you get like fewer poles, but they would not correspond to diagrams. You would. No. Well, even here, even for the full object, you cannot do it. Well, in case you are happy with one loop square as a diagram, then you can do it here. Is one loop square good? Okay. Yeah, maybe one loop square is a good diagram. But these objects probably will not have even that. So if you partition fraction them, you get some objects. But exactly, once you start to partition fractionate, you can actually generate new types of divergences term by term. Yeah. So it's not probably a good idea to partition fractionate. Like here, yeah. So if you take this object and you start to partition fractionate, you get double boxes and one loop square, and you generated higher IR divergences term by term. So, but here you can probably get even worse things than some spurious IR divergences, exactly from colliding these points and so on. So the objects only make sense as the full geometry, like full thing, because then we are guaranteed that they have nice properties. Once we try to expand them, I have no control what the individual pieces would look like. Okay, good. So, so here we do an ad hoc approximation because we know how to calculate integrands which don't have any internal cycles, like these ones. Okay. Now, actually, in some more recent work, we know also how to calculate integrands which have one internal cycle to all loops. Yeah. So you give me to any loop order. Actually, these guys, which we call trees, because they don't have any internal loops, they are very simple, and the numerators for these graphs are just given by products of two loop numerators. So here for that one, we can write n2 over d2. So this is a two loop numerator that we would get here. And there is a denominator between them. And for free loop, you just get n2 between lines a, b, and c, d, if this is a, b, c, d, and e, f. And then n2 between c, d, and e, f. So for everything what looks like a tree graph, the numerator factorizes immediately in terms of some two-loop objects. Yes? I cannot solve it geometrically. The only way how to solve it is to exactly... Okay, so let me just say, what we calculated, we were able to calculate for these integrands, it was not triangulating these geometries. I don't know how to do it. They still look too hard. But you can kind of use a hybrid of unitarity methods and this geometry, and just to fix the numerator. The numerator must be dual conformal invariant, has certain weights. So you just impose enough constraints on the numerator where it should vanish, and you fix it. And for these trees, it immediately collapses to the right answer. For these loops, it's more complicated, because this thing with collapsing already happens here in this diagram. So you have to impose on the numerator that it does not happen. And then it fixes, yeah, and you can fix it, all these things with one cycle. Once you have two and more cycles, in principle it works, but I don't have a closed form solution. I did it like for one object and so on. But here you have closed form solutions. And remember from the beginning of the talk, we would like to do things at all loop order. That's our, even if it is just some simplified version of something, we would like all loop order. So we have to solve it to all loop order. And these guys we can solve to all loop order. These guys for integrand as well. But these guys are so simple for these trees that you can actually do also the integrals. Yeah, you can find a differential equation and do the integrals. Yeah, which I guess I will outline in the last 10 minutes. No more questions. No, a priori there will be not reasonable. Yeah, so these things which are trees have even a subset of objects which are just ladders. Yeah, so now not ladder integrals by ladder geometries, but they share some property with the ladder integrals. So the structure of internal propagators is the same. Yeah, just all the other propagators are different. So if we have ladders, yeah, so these are geometries which look like that. So I only impose, let's say this is AB1, AB2, AB3, AB4. So I only impose these inequalities between adjacent loops. Now, if you look at the integrand, so there is some numerator, and then the propagators are AB1, AB2, AB2, AB3, AB3, AB4, and then there are all the propagators which involve just one of the loops. Yeah, AB1, 1, 2, dot, dot, dot. If you only look at this, this looks like a ladder integral. Yeah. The only thing is that it's not a ladder integral because all the rest doesn't match. Yeah. The ladder integrals has fewer of these propagators. This one has all of them. Yeah. So it's not a diagram, but just looking at these internal propagators, it has the structure of ladder integral. Which yeah. If you kind of ignored all these external, look only at the internals, it looks like ladder integral. Yeah, it doesn't cancel. No, no, no. It doesn't cancel. Yeah. Yeah. No, this is a chain. Yeah, yeah. No, I'm just saying ladder. Yeah, just if you had an actual diagram and you kind of connected the internal points, this would be the same. But so just from the point of view of these internal propagators, there is this similarity. But this guy has only 3 other propagators. That one has only 2, while all these guys have 4. Yeah. Yeah, Tomek is right. I can kind of take the numerators. Here they are very simple, and I can expand it, but it will still not get only diagrams. Yeah, you get kind of non-planar ladders. Yeah, things when kind of, because what does make the internal planar, the diagram planar? It just means that kind of there is a conspiracy between which propagators are allowed for this loop, this loop, this loop, and this loop. But somehow these loops don't care about the neighbors or so on. Yeah. So yeah, there is no such a coordination between these propagators such that they make a planar diagram. Anyway, so so these ladders have simple integrands as well as all trees. So the trees are different because they just don't have an internal cycle. You can still kind of map it to some diagrams. Yeah, so there are certain Feynman diagrams, or the diagrams in the expansion, where the sequence of internal propagators will not have internal cycle. But for the diagrams, it doesn't seem to play a major role which one are of this form. But for these geometries, it plays a role. Because these guys we can solve for all integrands, while once you start to have these internal cycles, yeah, we cannot in principle. Okay, but but let me move forward. So let me do this ladder approximation. Okay, I actually there is one more step. So here, so far, we are just at the level of the integrands for logarithm of the amplitude. So as we said in the beginning, in order to get this is the divergent object. In order to get IR finite object, we freeze one of the loops. So we make it a marked point, and this will not integrate over. Yeah. So for example, this is a marked point. We will not integrate over that, but we integrate over these two in these pictures. And this exactly gives this Wilson loop. So this happens to be once we integrate. So we integrate over those. So this is a function of one variable. The variable is a cross ratio of the loop we don't integrate over. Here it's an AB, 1, 2, AB 3, 4, over AB 2, 3, AB 1, 4. So there is only a single cross ratio. Yes. Doesn't have to be just this one. Yeah. You can also put it here. Yeah, you have to sum over everything. You have to. Yeah, you have to. Yeah, you have to. Now, if we did it so this was for this our single geometry. If we did it for everything, so for the integrand for the logarithm of the amplitude, if we integrate but freeze AB, we exactly get this null polygonal Wilson loop with Lagrangian insertion divided by empty Wilson loop. Yeah, and this object, this is this f as a function of z. This is at L loops. If we kind of dress it with couplings and resum it, this would be function of coupling and this parameter z. Okay, so this, which we define independently in geometry, happens to be the same thing as that. Yeah, of course, by Wilson loop amplitudes correspondence, it had to be the case because the log of the amplitude corresponds to that. Yeah, but so this is the object we are actually calculating on the physical side. But here on the geometry side, we are just freezing one of the loops and integrating over the rest, and get an IR finite function of 1 cross ratio. And this is at each order, at each loop order. The question is if we can resum it. Okay. So the thing that we would like to consider is some approximation to this function of g and z, which would be sum from 1 to infinity, some dressing with g. And then we consider these ladders. There's one extra step. Matthias was right. I have to also consider that the frozen is somewhere in between, but there is a relation between. You can always write any graphs which has one frozen loop as an using just the thing which kind of has this frozen thing stick out of that. Okay. There is an exponential, well, I forgot on which side is the exponential. It's between generating function and, yeah, sorry. Yeah, I think this one is exponent of, this one, I think, yeah. Okay, so you can always rewrite it just in terms of those. So we can resum of that. And so these guys are actually very simple. So this, even if you calculate this at one loop, so there is like a little bit shift of loop orders. This was a 2-loop integrand, but we are not integrating over that, so it's a 1-loop integral. This will be just log square z plus pi square, which is exactly the 1-loop contribution to this Wilson loop. And these guys are actually only functions of log square z and pi square. Yeah, so each of them is just log square, contains only log square z's and pi square. So these are very simple. And so we can actually here resum them directly. But one thing which is useful is also to use a differential equation method, because we can actually find the integrand is so simple that we can find a differential equation which tells us that if we act box of z, so okay, let me write it like d square of z, so there is some differential operator on this object, it just cuts one of the loop. Yeah, so so this just gives a lower loop order object on the other side at the left. Yeah, so this is a very, so you can just solve. So then this operator actually applies for the full ladder integral. So there is a differential equation for the full sum because you can apply it for each term in the expansion. And this gives some simple function of the log of z, which is just cosine of square root of gz logarithm of z over cosh of square root of 2g pi. Anyway, something in the denominator. So it's just a sum of logs, yeah, and it resums into that. So this is a very simple thing. If you expand it at strong coupling, so now this is a full sum. If you go with g to infinity, this just goes like e to the minus g. Okay, so it goes the same thing as you would sum the ladder diagrams. Okay, so it's not that surprising because this is kind of a topology of, as we discussed, of the ladder diagrams, and we resum it and we got something like that. Okay, but now we can resum one more thing. We can resum all the trees. Now the individual trees are more complicated, but the whole sum also satisfies some differential equation. So these objects are all of the tree diagrams from our expansion. And this is some interesting function which right, could be, but I'm using right. There can be, but there is a connection between. There is some exponent, yeah. So you can write the sum of all trees as an exponent of the ones where this thing is sticking out, yeah. Yeah. So yeah, it can be anywhere. Yeah, I'm just kind of representing it here like that. So there is some function which is relatively simple, but cannot be kind of right. I don't know what's the right name. This A satisfies some equation. But there are some cosines, some linear things. So we cannot really solve for A kind of explicitly in terms of G. So it's this function with this condition. Anyway, but we can expand it at weak coupling, strong coupling. Of course, weak coupling, we get what we expect. But at strong coupling, G goes to infinity. This function gives a constant piece. So there is something like z plus 1 over z over 1 over z square plus some expansion in 1 over g. So let me here just for reference write how the actual F looks like, the strong coupling, what we know from ADS-CFT. I already said before, it grows like G at strong coupling. So this one doesn't, yeah, so yeah, so the correct thing has here G, and then there is some Z over Z minus 1 cube. There is some log of Z times 1 plus Z. Anyway, it's maybe not that important. I just wanted to show that these are relatively simple things. So 1 minus Z. And then there is some term which is O1 and 1 over G expansion. Anyway, so our ad hoc approximation, which before that would again go nowhere, didn't give the right leading order contribution, but at infinity it goes like O1. Yeah, so not great, but not very bad like this. Yeah, so something in between. Yeah. So I think this wasn't calculated, the subleading actually. So we have nothing to compare here. Yeah, only this one was calculated. Maybe you calculate? Sorry. No, there was also some other. No, but somebody calculated it. Yeah. So, but the subleading wasn't calculated. Yeah, actually recently heard from Fernando Aldai that he tried to calculate, it was too hard or something. Yeah, I'm not surprised. Yeah. Yeah. It's the strong coupling picture. Yeah, with the minimal surfaces and yeah. Yeah, so we got this. Okay, so then you can kind of speculate if we add more things, would they all go like O1 and only if we see some totally everything, it goes like OG. This would be like a naive expectation because we took more diagrams than here, but in principle it's a measure zero diagrams. It's just a small subset. At L loops, most of the diagrams have internal cycle, almost all of them, 100%, like asymptotically. So we got this. But okay, so that would be not that surprising. We got kind of intermediate result, not negative, but not complete discovery positive. But now the surprising thing is the contribution to gamma cusp. Yeah, because and that's the last thing I will say. Now, okay, I will also say that with Lance and my students and Shruti, we are now trying to do another resummation because we know how to calculate the triangle like this geometry. We have explicit function in terms of polylogs. These are some simple HPLs. So we are trying to resum this. Yeah, this is a totally ad hoc thing. It's just because we cannot calculate anything else than this. So resum everything that, dressing with couplings, and see how these things behave. Yeah. So this is within a reach. Yeah, this satisfies some differential equation when this is a source term. So this is totally ad hoc, but this is something we can at least calculate to all loop orders to see how this behaves with comparison to just trees. Here we have a cycle, but it's a triangle. We could also have a box. You can say, why don't you do something else? Yeah, we don't know how to do something else. Yeah, so the only thing we can do. So we are trying to do that now with, as I said, with Lance, my students Umut, Tara, and Shruti. But the last thing I wanted to mention is this contribution to gamma cusp. Because we said that you can go from this function to just gamma cusp. Yeah, it involves some integration over z. You basically have to integrate z over some unit circle. And then you can look how the gamma cusp we know from all sides. Using BS equation, we can expand it, weak coupling, strong coupling to any order we want. So we can ask, what is the relation between, what's the contribution to gamma cusp we get here? Okay, so the gamma cusp at strong coupling goes like, with some choice of parametrization like 2g, and then there is 3 log 2 over 2 pi, and then there is some 1 over g expansion. Okay. Now, if we sum, if we now take these trees, which kind of failed to get the right picture, and we calculate the contribution to gamma cusp of the trees. The way how to extract the gamma cusp is slightly more complicated. So the fact that this only went like 0.1 at strong coupling doesn't mean that it contributes to gamma cusp at 0.1. Actually, the contribution is at order g, and the explicit formula is 8 over pi. And then it has some other pieces, which was like shocking numerics. First was shocking that it had the same order already. But the other one, that the coefficients are not that completely off. Yeah, this is, this might be a total accident, but this is like, I don't know, 2.5 or 6 or something like that, yeah. So, so it's very puzzling. There are these tons of other diagrams that contribute. What do they do at strong coupling? When you sum all of them, you should get 2, yeah. So, so this is also one of the motivations why we want to do that. We would like to see how it behaves at strong coupling for gamma cusp, and see, yeah, what is the hierarchy of things here. Yeah, so the hierarchy of these diagrams for the actual Wilson loop or this f function seems to be that you kind of need all of them, probably, to get the right behavior. I'm not sure, but somehow suggestive, despite already this sound gave something. But for gamma cusp, it's a total mystery, because it seems that things are at the same order once you do this sum. So we are trying to calculate that, but we we are a little bit stuck at one point. This is probably just, probably just a mistake. But once we extracted gamma cusp from this kind of triangle resummation, we seem to get things which are even stronger than the full result. Yeah. Which would be super puzzling. I don't know. That would be like a total, but this might be just wrong. Yeah. This might be just wrong. Yeah. That we have a mistake somewhere. Yeah. Yeah. So, the way how you get the gamma cusp is using some differential equation. So there is some g that you act of the full function of g, and yeah, and then you cannot expand in g before you solve the equation. So therefore, in the actual formula, yeah, you get. In other words, it seems that it goes just from some corner of the space. So there is some corner of this parametric space when things go like G, but for like special, I don't know how to exactly think about it, yeah. But it's in bulk, it goes like that, but some corner of the space, it can extract the G behavior. Yeah, yeah, I can write the explicit, yeah, the differential equation looks like this. So there is G ddg on gamma cusp is equal to the integral from minus pi to pi of this f function, where z is e to the I phi. You replace z by e to the I phi, integrate over unit circle, and this should correspond to g ddg on the gamma cusp. Yeah, and this integral, if you do it on this explicit solution, this integral will start with g. Yeah, on the other side. Yeah, I think there is some order of limit in this integral. Yeah, there is some problem with that. Yeah, that first expanding in strong g and then integrating is something else than first integrating and then expanding in strong g. Anyway, so we are left with this puzzle, but this is good because maybe for the f function we will not kind of, this expansion will be what we expect, yeah, slowly converging, but with gamma cusp there is some hope that, well, there was always this question, does there exist any subset of diagrams which give you good approximation to gamma cusp? And the answer like looked negative. Everything contributes to gamma cusp at 4 point. Everything is divergent. All of them contribute. You can never approximate it using ladders or some other diagrams. But maybe these negative geometries kind of pinpoint that these things which have fewer propagators are somehow more divergent in this 1 over epsilon square, and they kind of made it better, and the more complicated ones will just, the contribution to gamma cusp will die. Yeah, that's kind of speculation, optimistic. Yeah. Okay, I'm over time, 10 minutes. Sorry for that. Thank you. Yes, Tomek. Ah, yeah. I don't know, because we are not doing it as a resummation of individual things, but solving this differential equation. So this is a solution with... Yeah, but it's a sum over all. I have zero intuition. Yeah. You might take a subset of those, which is more than that, and then try to... Yeah, maybe there would be most... Yeah, yeah. I don't know. Yeah. These diagrams are... just to see, these are HPLs. So here we are trying to resum some HPLs. We are running into some small difficulties, just technical that, yeah. If you expand HPLs and then you try to resum each HPL separately, it's divergent. So somehow it's only this collection of HPLs, which gives something finite, which we can show like numerically. Yeah, but these are simple HPLs, so we thought that we would just kind of turn them apart and then resum each class of HPLs, but that kind of didn't work. Yeah, we have to sum some, yeah. Yeah, it seems like pi is spurious pi. It's like a spurious pole in 1 over pi. Yeah. Maybe, yeah. Right, right. Yes. No, but you can think that there is some, maybe, yeah. I don't know. I think about it as a spurious pole, yeah, in the pi at strong coupling. Pi goes to 4, yeah. Yeah. So, yeah, so we actually do, we are doing something for 5 point with Johannes and Dima Chicherin and some other people in Munich. And yeah, for that case, there are some just technical things that the thing depends on more cross ratios. So we are actually bootstrapping kind of the symbol from that. Now there are prefactors in front of it, yeah, because here all the prefactors are 1. But now if you integrate, so if you integrate these things, there are some universal function, which is kind of an integrand for the 1 loop amplitude times some transcendental. At 5 point, there are several of these functions. So there are kind of different leading singularities. And the integrand is slightly more complicated, but we have the integrand, we have differential equation. There is something funny with the symbol letters. Yeah, that you probably, they also communicated with you, yeah. So there is something funny with the symbol letters. Actually, just very recently, Dima was able to, so we are doing these we only do these letters because I now suggested we also do trees, but so we try to do letters, these letter geometries. Yeah, and of course there are also some results in the literature. So for 5 point, I believe the 2-loop result is complete. So this is a sum of this plus this. Multiple variables. Multiple. I forgot how many cross. 4, and you can cook up many. Yeah. For variables, you have. Yeah, and so this one we calculated. So this whole thing was calculated before. So then we broke it into two of these negative geometries. Interesting thing is this is just, yeah, also there is this thing now. Now this cannot be simply kind of absorbed by that. This thing has more leading singularities. This is just 1 loop square. This is because you are not integrating over the middle one. You are just integrating this and this separately. These 2 loops don't talk to each other. So this is 1 loop times 1 loop, but the number of leading singularities is bigger than you have in the final answer. Yeah. Here is also the number of leading singularities is bigger. Yeah, it's like 10, and the whole thing has only 5. Yeah. So the leading singularities are spurious. However, the actual functions, if you look at the symbol, how many different symbol entries you have? You have massively less here and here. This is just 1 loop square. This is also very simple, and this is the most complicated one. Yeah. So it kind of breaks it into simple sectors based on the symbol letters, but not necessarily the leading singularities. Now, I think just like 2 weeks ago, Dima calculated 3-loop chain. But there were some new symbol letters which were needed from what he was expecting, because also we are outside the planar objects. So it's not completely clear which symbols to consider. So he considers some non-planar symbols, but it's not really non-planar in the usual non-planar sense. Yeah, it's still dual conformal invariant. Yeah, so okay, anyway, so there is something interesting for 5 point, but more like exploratory, like from the point of view of symbol bootstrap, because I am not sure if we would be able to sum this, yeah, because this would need, yeah, to calculating the ladder too. But anyway, we know that at strong coupling, it's kind of ignorant to the number of points. So I still expect it will behave badly here. Yeah, okay.